before I forget, um, I want to, because the asynchronous lecture was on colligative properties, and we didn't get to go over those, and I kind of just did one example, maybe two for each concept. I just wanted to go through that again more slowly and do more problems for each concept and try and really root that in more. And then the plan is Thursday. I will have some kind of review. It'll probably have to be an asynchronous video again. But what I'll do is I'll have a recording of just the different stuff that will be beneficial to know, right? So taking all of our slide decks and condensing it down into one slide deck with the highlights. Okay, that's the plan for this week. Now, if you are still needing help with the lab today or the ICA for you section 1 folks, feel free to see me tomorrow at 12 for office hours. Section 1, you're going to be doing the freezing point depression lab tomorrow. And so, yeah, we'll just see how it rolls. But that's the plan for this week. Okay. Next week, next Tuesday, will be the midterm. No lab that week, or no lab that day. And then Thursday, we'll get into entropy and the second law of thermodynamics. And I think, what do we have for that lab? I think that there's a journal club. Yeah, we'll do our third journal club. So I may switch that around a little bit because I don't want you guys to have to juggle reading this paper and then also studying for the exam. So probably what I'll end up doing is I'll move the ICA research project up to week 7 and move the journal club 3 down to week 8. That way I don't want to max you guys out. Okay. All right. Any other questions, comments?
Are we going to talk about the format of the midterm, or is it basically just the same as it was from the first quarter?
I don't know. I'll have to look at Sean's, how he formatted his exam, and then go from there. I can definitely give you guys. I don't like to have my students go into a test blind and not knowing what to expect. So I will definitely, during the review on Thursday, we'll give you guys some hints. I've never done an exam like a midterm for chemistry. Well, I guess I did one in Chem 103, but how did Sean have it? Did you guys, were there just questions and then you wrote it out and then you submitted it? Or were there like drop down, or was it a mixture of those? Do you remember?
I remember. There was a practice exam which had questions that were almost exactly like the test, but like with different numbers and like compounds or whatever. Mm-hmm. And we first did that, and we were able to like try to do it on our own, but we were allowed to talk with like other people, the tutor and Sean. And then the test was like a file that you open, and then you just like did the answers on a Word document or paper, scanned it, and then turned it in.
Okay. Yeah, that's probably what I will do. I think that would be better because it's basically calculations, right? And that's hard to do in Canvas. Did you guys like that?
I thought that was good because then you can like work stuff out on your own sheet. Yeah. And also I was wondering, is it open note, open book also?
Well, was it open note, open book for Sean?
The
whole thing?
He said that he would prefer us to not use our notes, but there's no way that he could tell if we did. So like, it's basically like you can do that because there's no way I can find out if you did or not, but I would like to know that for your own sake in learning that you're trying to do it with just the information provided on the test.
Yeah.
I
Okay.
think the idea was that it was, like, fast enough that we weren't gonna look through all of our notes, but, like, we were allowed to look at them.
Yeah. So in the past, I've definitely timed these exams so that, especially with classes where it's not calculations, where it's just like when I taught micro last quarter, you can easily just look at the slide deck and see an example of a gram-positive bacterium, and so with this class, because there are calculations that you have to do, and Sean and I both have a precedent of giving you guys pretty much all of the equations, at the back of the exam. Yeah, I mean, I would say that I wouldn't rely on your notes, but do you need to memorize that delta TF equals KFI molality? No. Right? Do you need to memorize all of these equations that we've talked about? No, because that's not important. What's important is how you utilize those equations, right? And so that's not something you can get in your notes. That's something you get by practicing, by doing the homework, by doing the ICAs, by attending lecture. So yeah, I mean, I would like, there might be some things. Yeah, I would say that I would prefer you not use your notes, because that will slow you down. The test will be timed. But I agree. I'm not going to use what is it called? I'm running a blank.
That thing that monitors whether you open a different tab.
Yeah.
Proctorio.
Proctorio. Thank you. I'm not using Proctorio. I feel like it's clunky and it's kind of big brothery. And so it's on you to be familiar enough with the material that you don't spend too much time combing through. Okay. Yeah. Okay. Yeah. So, I mean, I imagine it won't be too much of a deviation from Chem 101, because I really try my best to have continuity through these different courses. So anything else?
As far as calculators goes, I mean, what kind of calculator can we use? Is there any restrictions?
Same calculator you've been using this whole time. So if it's a Texas Instrument, if it's your cell phone, that's fine with me.
Awesome.
Yeah. No using, like no posting questions to blogs. I mean, in fact, you're not going to have enough time to do that, so but yeah, none of these equations will require a high computing fancy calculator. So just use whatever you're familiar with. Don't get a new calculator and then try and figure out how to learn to use it and then get flustered. Use what you're comfortable with. Anything else? Now is a good time to talk to me, because like I said, the lecture on Thursday, I won't be around. I'll be around tomorrow from 12 to 1, and of course I'll be around before the exam. But if anything else comes, just shoot me a message, any other questions or concerns. And then
I have a question. Are the asynchronous meetings going to become a routine thing?
I hope not. The problem is that I need to pick up my kids from the bus. Even if I pick them up from school is 1:30, the bus is around 2. So it's right in the middle of the lecture. And so we wouldn't be able to, we'd miss a big chunk of the lecture. And so on the days that my wife's home and available, she can pick them up and I can do a live one. this Thursday, I actually have to go out of town. I need to take a family member down to SAC to see a doctor down there. So I definitely won't be around this Thursday, but might be hit or miss, unfortunately. Okay. Anything else, guys? All right. Let's do this thing. Let me find the slide deck. Slide deck is in Canvas. If you want to follow along that way. Let's see. Okay, so colligative properties continued. So as a refresher, molarity is moles of solute over liters of solution. So capital M. Oh, it always does that. Molality is lowercase italicized m. That's moles of solute over kilograms of solvent. Okay. Then we have mole fraction, which is the moles of some component that you're looking at, whether it's the solute or the solvent, over the total moles of all components. So moles of A, that could be moles of solute over the moles of the solute and the moles of the solution. And that gives you the fraction, right? So how much of that is in the solution. And so these are the ways that we express concentrations of solutions, okay? And then we can get into mole percentage, which is, the mole fraction times 100%, okay? That tells you how much of that is in there. So again, if we were doing a problem that was talking about, a 10% sugar water solution, you could backtrack from that percentage to the mole fraction and calculate that and get to whatever they're asking for, whether it's the grams of the initial solute or whatnot. And this is just a table that, again, kind of outlines all these different expressions, right? The difference between molarity and molality and mole percent and parts by mass. And we're not really going to do much with the ppm and the ppb. It's just there for your information. Most of the stuff we're going to focus on are these first three up here: molarity, molality, and mole fraction. Okay. So here we go. Perfect case. Here is something that is the molarity of a, oh man, sorry, my contacts just got all messed up in my eyeballs. The molarity of 6.56% by mass glucose solution. What is the molarity? They give us a density of 1.03 grams per mil. How would you guys set this up? Well, for one, we just, because it's a percentage, we designate it with this arbitrary grams. We could say that, well, if it's 6.56%, that would be 6.56 grams out of 100 grams, right? To give us that percentage. And so I need to take these contacts out of my eyes because for some reason they're messing me up. I'm going to do that really quickly, and you guys work on this problem, okay? I'll be right back. All right, guys. Let me tell you, being a glasses wearer in the age of COVID really stinks, because you don't want to wear glasses with your mask, because then your glasses fog up. So you wear contacts, and then somehow I flipped the contacts up underneath my eyelid, which if any of you have done that before, you know that that is excruciatingly painful and unpleasant. But I finally was able to dig them out, and let's do this problem, okay? They're saying it's a 6.56% sucrose solution. All right, let me make sure. Yeah. Okay, 6.56%. C6H12O6, right? Yep. Okay. And they want to know the density, 1.03 grams per mil. And they want to know molarity. Okay. What do you guys think? What do we do for this? First week, it's a percentage, right? So we can get it out of that percent. Let me pin my thing here so it's nice and big for me at least, right? So we can say 6.56% is essentially 6.56 grams over 100 grams, right? What else? What else can we do?
Do you multiply by the molar mass of glucose and then the density?
Yeah. So 1 mole over, what's the molecular weight of C6H12O6?
I looked it up and got 180.16.
181.6. And then,
Sorry, 180.16.
oh, okay. 180.16. And then, yeah, we have 1.03 grams per mil.
Don't we want the milliliters and liters?
Oh, okay. Well, we will definitely will want that, right? Because molarity is moles per liter. But we have, so we can do that calculation in there too. So we could say 1.03 grams per 1 mil times what to get it to liters?
One liter over 1,000 milliliters.
Yeah. Although actually, you know what? I think, okay, so here's grams.
Or the flip it.
Yeah, we need to have this flipped. 1 mil, 1.03 grams times 1 liter, 1,000 mils. How does that look? So then what do we get for that?
Wait, so when you're doing the 1 mole over 180.6 grams times 1 milliliter over 1.03 grams, what does that become, since the moles don't cancel out the grams?
Eventually you want it moles per liter. So
So how does that 1.03 grams get canceled out?
Well, good question. Maybe let's start here first. Let's just get the moles of our sugar. So what's 6.56 divided by 180.16?
0.036.
Okay, so those are our moles. What else can we do? We say that it's 100 grams, right? It's in 100 grams of the solution. So we could take 100 grams of the solution times what? Now we're wanting to get to liters. So times the density, 1 mil over 1.03 grams. And so that is going to cancel out our grams. And then we want to convert 1 liter over 1,000 milliliters. So now our grams cancel, our mils cancel, and what's that? 100 divided by 1.03 divided by 1,000. What do we got? Anyone?
0.097.
0.097. Did I hear that right, Ryan? Is that what you said? Okay.
Yeah.
So what's molarity? Again, it's moles over liters. So we have our moles here, 0.036 moles over our liters, 0.097 liters. And what does that give us? That should give us our final answer.
.371.
I set it up like what you did on the top, but then I just multiplied that by 1.03 grams of solution over 10 to the negative third liters. Is that okay too?
Yeah. 10 to the negative third is 1 over 1,000. So absolutely.
Great.
So that would be our molarity if we had a 10% or a 6.56% sugar solution. Okay. Let's go on to another one. Antifreeze in most automobile radiators is a mixture of equal volume ethylene glycol and water, because ethylene glycol lowers the freezing point with minor amounts of other additives. What are the mole fraction and molality of ethylene glycol? And they give us a solution of 2.22 times 10 to the third grams of ethylene glycol and 2.00 times 10 to the third grams of water. Approximately 2 liters of glycol and 2 liters of water. Okay, so again, when you are faced with a problem like this, you have to pull out the information. Get it out of that paragraph there, right? So what do they want? They want the mole fraction, and they want molality. Okay. What's molality? That's moles over kilograms. And what do they give us? They give us ethylene glycol, C2H 4OH2. And they give us water, H2O. And they say that it is the ethylene glycol mass is 2.22 times 10 to the third grams, roughly 2,000 milliliters. They're not giving us the density of ethylene glycol, so we can assume it's close enough to 1. And then water is 2.00, I think. Yes, times 10 to the third grams. Okay. Set this up. See how you do. You're given grams. From grams, you can get to moles, right? You get moles of your solute, which is the ethylene glycol, over kilograms. And from there, you can do mole fraction. Or you can just do mole fraction by just getting the moles of these first. So anyway, give you a little bit of time to work on that.
So Daddy?
Yeah?
When you're done with your lecture, could you put my batteries in my camera?
Yeah, I can.
And Daddy, do you still have that little, like, tiny dry erase board down here?
No, I don't.
Oh.
They're both upstairs.
I'm happy to be back in school. I bet you're happy to be back in college.
I don't know.
You know something that all 3 of us can enjoy?
What?
Summer break.
That's true.
I see you can do that on your computer too.
Mm-hmm.
So is it like your computer and your iPad is connected to each other? I know that this iPad and Mama's phone are connected, but what about?
All right, how we doing, guys? Still working? What did we get for the molecular weight of ethylene glycol?
$62.07 grams.
And in water is about what, 18 something?
18.0.
18.0. Okay. So 2,220 divided by 62.07 for our ethylene glycol, and 2,000 divided by 18 for our water. What do we get there? What do we got?
I got 35.76 moles of ethylene glycol and 111.11 moles of water.
Okay, is that what everybody else got?
Confirmed.
Okay, so then what do we do next? Should we do mole fraction since that's the first one they're asking for?
Yeah.
Okay, so mole fraction would be 35, so X equals 35.76 moles over the sum 35.76 plus 111.11. And what's that?
I was a little confused on mole fractions. Which part do you put on like the top of the fraction? Like it was written as mole A in the slide. What's mole A mean?
It depends. It can be whatever. So in this case, since we're putting 35.76 moles on top, that's going to be the mole fraction of ethylene glycol. Okay. If we wanted to know the mole fraction of water, we'd put 111.11 on top.
So it depends on which substance you want the mole fraction of.
Exactly. There you go. All right. So what is that?
My percent might be off, but it's 0.2435 or 24.35.
0.2345.
2435.
Sorry. Okay, then yeah, if you wanted to do the percent, you would multiply by 100. But just for the mole fraction, we can say it's this right here, unless anybody else has a different calculation. Okay. Now, so that's A. That's the mole fraction of, well, let me make sure they're asking for ethylene glycol. Yes. What are the mole fraction and molality of ethylene glycol? Okay. How would we get the molarity or molarity? No, molality. It wants molality. Okay. So how would we get the molality? What is molality? I already have it written. Moles per kilogram. So we already have our moles, right? Right here. 35.76. 35.76 moles. Now we just need to get the kilograms. How do we do that? Kilograms of water. What did they give us? They gave us grams of water. How many kilograms is 2,000 grams?
2 kilograms.
2 kilograms.
Hey, I was doing 2 before.
You were
said
doing,
2.
you knew that, Bennett?
Mhm.
Great.
I was doing 2 before you said 2.
So 35.76 divided by 2.
17.88. 17.88.
Okay. Great. And we got to figure out how many sig figs for these answers. Sig figs are important. Looks like they give us 1, 2, 2. Okay. Cool. What's the next one? Fraction.
Sorry, what did you just figure out for sig figs?
So what do you guys think? In that problem, it gives us 2.22 times 10 to the third grams of ethylene glycol, and then 2.00 times 10 to the third grams of water. So how many sig figs would we use here?
Do we only have 2?
3, right? Because it's 2.22, that's 3, and then 2.00, that's also 3.
Okay. So will we just round this to 9? Okay. Now, does that make sense to everybody?
Yes.
What about rounding the mole fraction?
Yeah, so this would be 0.244, right?
That's what you do.
Okay.
It does not look like it.
Now you could argue, right? This is in the hundredths place. Now we're going into the thousandths place. Can we do that with sig figs, or do we stick with the hundredths? Bennett says the hundredths.
It stays at 0.244.
Okay, hopefully that makes sense, guys, because that could be a good test question, something like that, you know, where you're given something and you need to find the mole fraction and the molality of something. I haven't made the test yet, but I'm sure that there'll be something similar to this on there. Okay. What else we got? We got a couple more problems here, and then we can devote the second half to boiling and freezing and pressure. What are the
units? Is the units for mole fractions moles per mole?
Yeah, it was just canceled, so there isn't a unit for a mole fraction.
Okay.
So let's do it a second time just to burn that in, okay? Mole fraction and molality of a solution that contains 0.850 grams of ammonia dissolved in 125 grams of water. Yes, Bennett?
Are we going to show them the tea feeder?
The what?
The tea feeder.
Oh, no. Bennett was asking about, we like to make Rube Goldberg machines around here. They're fun. And so we made one recently that serves tea. So I don't know if you know what a Rube Goldberg machine is, but think about the game Mousetrap. It's a series of different functions that lead to some goal that is pretty mundane. So the process is way more complicated than the service that those processes carry out, which can be metaphorical in a lot of different examples of life and bureaucracy. Anyway, so molarity, mole fraction, and molality. So they give us ammonia is 0.850 grams. Water is 125 grams. Same thing, guys. Just different constant, different amounts and different things. Why don't you go play with your brother?
He doesn't want to play with me.
Well, why don't you go play something by yourself? I'll play with you when I'm done. Okay. Whoever has the answer, whenever you get it, just shout it out.
Hey, Daddy,
Yes, buddy.
I think with those coins and cents, I think I have $100 maybe.
Cool.
I don't think that looks like to cross country ski. There's no snow.
What do you think, guys? What's the molecular weight of ammonia?
17.03.
Okay. So what's 0.850 divided by 17.03?
0.0499.
Awesome. Moles. And then what's 125 divided by 18?
6.94.
Great. What's our mole fraction? They're asking for mole fraction and molality of a solution of a, so what are the mole fraction of a solution that contains? So this doesn't say specifically. So in this case, Hannah, we should do it for both, okay? We could say that the mole fraction of ammonia is 0.0499 moles over the sum 0.0499 plus 6.94 total moles.
I have a question about rounding. Is it better to round everything for sig figs at the end, or is it okay to do it at each step?
That's a good question. That's a philosophical question.
Oh, okay. So it
You'll
sounds
get,
like when you say it's a philosophical question, it doesn't matter.
well, it doesn't matter to me, okay? Some people will say, you know, based on if you have a multi-step problem, you need to do that after each calculation. Some people say round at the end. Okay. I'm not a stickler, so I say, do whatever.
Okay.
Okay, so what's this?
Did you add up the moles of the whole thing because it said of the solution, or do you always do that?
No, you always do that to get the mole fraction, okay? Because just think of it as like a percent. Like I want to know what my grade was. So if there are 100 questions and I got 95 questions right, and then 5 questions wrong, 95 plus 5 equals 100. That's the total. And it's just giving you essentially the fraction of what you got out of the fraction of the total. So that'll be like that for any mole fraction calculation.
So it's moles of solute over the moles of the whole solution, not moles of solvent. Is that right?
It can be. No. So in this case, because they're just asking for the mole fraction, they didn't say the mole fraction of the solute, ammonia. We're going to do it for both. So this is going to be moles solute right now. And what is that answer?
.00714.
Okay, that's the mole fraction of ammonia. But then we can also take 6.94 moles over 0.0499 plus 6.94 total. And what's that?
0.993.
Okay. 0.993 H2O. Okay. And as it works out, if you add up 0.00714 plus 0.993, you should get about 1, right? 100%. So those are the mole fractions. It also wants the molality. So what's
Okay,
molality?
I guess that's why I'm confused is that you're just adding up to 100%. So if it's asking for the solution, are you just giving 2 separate answers? But there's not like one fraction for the solution, right? Because that should be 100%.
Right.
Okay.
Yeah. I mean, maybe that might be not the best worded problem. Usually the problems, will say, what is the mole fraction of ammonia? Or what is the mole fraction of the water? Or what is the mole fraction of the ammonia and the water? This was a little bit more ambiguous. But yes, that essentially, when they ask for mole fraction, you're either looking for the solute or the solvent.
I'm just confused because I think I could be wrong. I might have written it down wrong. But on the last problem, didn't we just do the moles of the solute over the moles of the solvent, not the moles of the whole solution on the bottom? No.
If we did that wrong. For the mole fraction.
Okay.
For the mole fraction of that previous problem, it should have been the moles of ethylene glycol, because that's what it was asking for. It was asking for the mole fraction of ethylene glycol. It should have been the moles of ethylene glycol over the moles of ethylene glycol plus the moles of water.
We did do that. The wording that made it make sense to me for mole fractions was you're trying to find like the certain amount of moles of one of the components out of the 2 components, which is the total moles.
Yes.
Yeah, that makes sense. I think I just wrote it down wrong then. Thank you.
Okay. Thank you, Hannah, for your help. Okay, so what do we do to get molality? We already have the moles of the ammonia, right? So 0.0499 moles. Now we just change that to kilograms, right? 0.125 kilograms of water. H3, H2O, if you prefer. So what does that equal?
Point 0.00719.
Okay. Is that what everybody else got?
Did you take
0.0499 divided by 0.125. Okay.
I got 0.3992.
All right, I need a tiebreaker. Point 0.4. Okay, that's closer to
Yeah,
0.39.
0.4.
Okay. So thank you guys for your answers. Wrong or right, doesn't matter. We get to the finish line together. What did we say? 0.3399, something like that? Okay. All right, let's take
a 10-minute break?
let's take a 7-minute break because Matt likes to be, you know, on a nice rounded number. So we're gonna take a 7-minute break. Oh, now we're gonna take a 6-minute break. We'll be back at 2:10 and we'll go into some boiling point elevation, freezing point depression problems. Okay. All right. See you in a bit. Okay, guys, welcome back. So for the duration of our time together, I want to spend talking about Raoult's law, boiling point elevation, freezing point depression, and osmotic pressure. So Raoult's law is that the partial pressure exerted by any particular component, so just like mole fraction is mole subscript A, like Hannah pointed out, Raoult's law is P subscript A, because it's just whatever particular part of an ideal solution that you're looking at. And so it's relative to what's being asked. But anyway, the partial pressure is equal to the vapor pressure of the pure component, not in solution, multiplied by its mole fraction in solution. Okay, so X is the mole fraction, and the vapor pressure is P. And so we can predict the partial pressure by knowing those two values. Or if we know the partial pressure and the mole fraction, we can determine the vapor pressure, so on and so forth. So when we're talking with non-volatile substances, the vapor pressure is going to be negligible, right? Because that means it's not going to be contributing to the vapor pressure, because it's not going to be readily evaporating at room temperature. And so the vapor pressure above the solution, remember, which that's the gas molecules that are hovering above the liquid. The vapor pressure above the solution that contains only non-volatile solutes is due only to solvent. So meaning the vapor pressure is made up of the solvent by itself. And so in that case, we can say that it's not going to contribute to the partial pressure, the non-volatile solute. And so we can say that the partial pressure of the solution is equal to the mole fraction of the solvent times the vapor pressure of the solvent. Okay. So this is an example where we're going to be calculating the mole fraction of the solvent. So it's going to be on the numerator. Okay. So here's a problem. Calculate the vapor pressure at 25 C of a solution containing 99.5 grams of sucrose. And then they give you the formula. And 300.0 mils of water. The vapor pressure of pure water at 25 C is 23.8 torr, and assume the density is 1.00 grams per mil. Now, you probably all are aware that sucrose is a non-volatile substance, right? It can sit in those little shakers for a long time, not really go anywhere. So we can assume that the sucrose is non-volatile in this equation. What are they looking for? They're looking for vapor pressure. Okay, they give us vapor pressure of just water. And so see what you can come up with based on Raoult's law.
Sorry, what does the C stand for? Is that just the specific pressure?
20, there should be a degree there. No, 25 degrees Celsius. It's saying that the temperature, it's basically saying at 25 C, that's the temperature that this vapor pressure, that's what we're going to do our calculation for. And then they give you the vapor pressure of pure water at 25 C. 25 degrees Celsius is what it should be. They're saying the temperature is not changing, so you can assume that the vapor pressure of 23.8 is going to be relevant in this calculation because the temperature is the same. Okay, so let's write out what we've got here. We've got 99.5 grams of sucrose, 300 mils, 300.0 mils of water. And again, it says that the density is 1.00, so we can easily make that translation from mils to grams. The vapor pressure of water is 23.8 torr, and density equals 1.00 grams per mil. Okay, and that the temperature staying the same. So okay. So what's a safe bet to do when you get one of these questions? What, like, to hit the gates running? What are we going to do first? We have grams. We want to change them to
moles.
Yeah. Moles. Okay. So 99.5 grams times 1 mole over the molecular weight of C12H22O11. And then we can say 300.0 grams times 1 mole over, I know that one because we've been doing that for a while now, 18 grams, okay, for water. Anybody look up the molecular weight for sucrose, or better yet, calculate the molecular weight? Anybody?
$342.3.
Yep, I was just looking it up. 342.3 is what I got too. Okay. So do this, get the moles. 99.5 divided by 242.3. I got 0.29. 300 divided by 18. I got 16.67. Looking good? Okay. So those are our moles. Moles of sucrose, moles of water. It's asking for the mole, well, we've got to do the mole fraction of the solvent, right? Because it's sugar's non-volatile. So mole fraction is 16.67 moles H2O over 16.67 plus 0.29 total moles. And what's that equal? Anybody?
0.983.
0.983. Okay. So now we plug it into Raoult's law, which is P equals mole fraction times vapor pressure. So the vapor pressure is 23.8. So partial pressure is going to be the mole fraction 0.983 times vapor pressure 28.3 torr. What's that?
With this equation, does it matter what unit the pressure is in? Like, do you always want to get it to torr or atmospheres or something?
No, I mean, so in this case, we're not using any other like gas law constant that will have other units. The question you might get a question though, where it says the vapor pressure is 23.8 torr. What is the partial pressure in atmospheres? And so in that case, you'd have to do a conversion factor of 1 atmosphere over 760 torr.
Okay, so it's only if it specifically asks.
Yeah. If it gives you if it gives you one unit and asks you for a different one, then you'll have to calculate. But this is just saying it's not specifying that. So, but good to ask. Nice question. So what's 0.983 times 28.3?
It should be 3.8 right there.
Yeah, Carl, you transposed the number for the torr. It should be 23.8. You have 28.3.
Thank you. I think that was Rachel. Thank you. And Matt, I think, or somebody. Thank you, auto corrections. Okay, so my bad. 0.983 times 23.8. That equals what?
23.4.
That makes sense, right? Because you're multiplying this by almost 1, basically. So what we're saying is, when you make a solution of sugar water, you don't really change the partial pressure that much, right? But it does change a little bit. 23.8 to 23.4. Okay. Now, oh, no, that's the textbook. Here we go. How about this? What is the vapor pressure of 1.0 liters of water with 30.0 grams of sucrose? This time they gave us the molecular weight. The vapor pressure of water is at 22 degrees Celsius and 19.8 torr. So, what time is it? Do you guys feel like you have this? Would you rather, maybe we'll come back to this if we have time. And remember this problem, and I recommend you practicing this problem. And if you do it and you want to know the answer, we can go over it in office hours tomorrow. But in the interest of time, because I do want to get to some of these other ones, let's move on to boiling point. If we have time left over, we can come back. So as you guys remember, those of you in section 2, this morning we talked about boiling point elevation and boiling and freezing point depression, and it's the relationship and the change of the temperature of the boiling point, setting it equal to this constant, this boiling point constant times molality. And if it is involving a solute that dissociates from itself, like for instance, salts, then you have to have this Van Hoff factor, which takes into account the fact that 1 mole, for instance, of something is going to then dissociate into 2 moles of those respective ions, for instance. Okay. If it's non-dissociating, then I is just 1 and it cancels itself out. Okay. We only need to use I when we're dealing with things that dissolve and then dissociate as a part of that dissolving process. Okay. So if we say, what is the boiling point of a 0.33 molal solution of a non-volatile solute in benzene, what would we do for that? Well, let's erase this.
Can I ask a quick question about Raoult's law?
Yeah.
I'm just slightly confused about partial pressure still. I guess I'm partly just wondering, like in a word problem, if that was the part of the equation that they were giving you, would they specifically say that that is the partial pressure, or does it just tell you that like the solute has that pressure at a certain temperature? I guess, yeah, like how would it be worded?
Yeah, it would be worded like the partial pressure of this solution is 23.4 torr. What is the vapor pressure?
Okay, gotcha. So and it would give it to you for the whole solution, right? Not just the solute or the solvent.
Yeah, yes. So if it was asking for the partial pressure, then it would be explicitly stated that is this one here.
And sorry, can you give a quick explanation of the difference between vapor pressure and partial pressure conceptually?
Yeah, so when you have gases, they're going to exert a certain pressure on the system. And so think about with the vapor pressure, the vapor pressure is the pressure exerted by the solution, but that's also going to be in a system with other gases that are exerting certain pressures, right? And like the atmospheric gas. And so the partial pressure is just relating the pressure that is caused by that solution. So if you wanted to look at the total pressure, let's say you had several different solutions all together. Each of them are going to have different vapor pressures based on whatever those solutions are made of. And so each of them are going to be contributing to an overall partial pressure of the system. And so if you wanted to calculate the total pressure, you would add up those different partial pressures to get total. And I think you probably might have kind of gone over this a little bit in Chem 101 with the gas laws. I'm not quite sure if Sean did that or if he went into partial pressure or not, but that's the idea, is that it's just it's a fraction of the total pressure in that system.
Okay, yeah, we did go over that. It's just been a while, so I was trying to remember. So it's the same thing as vapor pressure. It's just one fraction of it.
Yeah, it's the part of the total. It's the part of the pressure in that system that is derived from the vapor pressure of that specific solution. And so when we say the overall pressure, Raoult's law, what it's doing is it's saying the overall pressure of that's exerted by that solution is equivalent to the concentration of that solution, the molality or the mole fraction, right? And its specific vapor pressure. And you put those together, and that's going to exert an overall partial pressure of the system. And then if you consider other things in that system also exerting partial pressures, then you can use those to add up the total pressure of that system. Because in this room, right, if I had a jar of sugar water, there's going to be that vapor pressure, right? And then that's going to exert an overall partial pressure in the system, but there's also gas in the room, right? There's carbon dioxide that I'm breathing out, there's oxygen I'm breathing in, and so those are going to have different pressures as well. And then I have my carbonated water, which is releasing CO2, and that has a vapor pressure, and so all of those add up to total pressure. Okay. So what will we do with a problem like this, guys? First we have our equation, right? The change in the boiling point is equal to I KB molality. And they're asking for benzene, and they're saying, what's the boiling point of a 0.33 solution? Okay. So what do we've got? We've got this, right? We got the point, what is it, 33. We'll need to look up the KB, which will be in, I don't think I have it. Well, did I put that? Sorry. Here we go. Benzene. So KB looks like 2.53. Okay. It's not dissociating. So I is 1. And that's it, right? That will give us our change. So what's that? What's 2.53 times 0.33?
Zero
0.8349.
0.8349. Okay. Now it's saying, what is the boiling point though? This isn't the boiling point. Anybody know what this is?
The change when whatever it was added.
Benzene. Yes, exactly. It's the change of the boiling point when you now make it in this solution. So we need to know what the boiling point of benzene is, which I think I have. Oh, let me get back to this. Share my screen. Where's the boiling point? Normal boiling point of benzene, 80.1. Okay. So we're saying benzene by itself is 80.1. But now, if we assume that we've put this solution in and changed it by this, then we just subtract, or what would we do? Would we subtract or add?
You would add because it's positive, right?
Because this is boiling point elevation. Now, freezing point depression, that'll be the opposite, right? Because we're decreasing the temperature. So what is it? 80.9 3.
Where did you get the 80.1?
So in that, in this chart here, this was right, this is in the slide deck. It's right before this problem. If you look right here, it has benzene. So here's benzene, and it gives us its freezing point. It gives us our freezing point constant. It gives us our boiling point and our boiling point constant. So that's where I got that. Okay. Cool beans.
Yeah, thank you.
Great. Okay. See if we have, how are we doing on time? Okay. The boiling point of a solution. Let's see. Do we want to do this one? I wonder. Yeah, why not? Well, that's how many do I have here? Okay, let's do this last one, and then we'll get into freezing point. No, we already did that one. That's in there twice. Sorry, guys. Let's do this one. 3.60 molal aqueous sucrose solution. So what do we need for that? You'll need to know the KB for, we're going to assume that it's water, because sucrose solution will just, if you see sucrose or glucose, just assume that the solution is the sucrose or glucose being solute and water being the solvent. So, oh, stop. I don't like it when Zoom beeps at me like that. Okay, so we got water here in this table, and the KB is 5.512. And they said that the solution, the sucrose, was, I think it was 3.60. Yeah. Okay. So the delta TB is going to be equal to 0.512 times 3.60. And what do we get when we do that?
$1.843.
Yep, that's what I got. Thank you. So that's the TB. They're asking for the boiling point. So we know the boiling point of water is 100. So 100 plus 1.843, 101.84. Okay, so that's what's going to take to boil water if you add that much of sucrose, 3.6 moles per kilogram. Okay. You don't necessarily include I when it's volatile. You'll only look at I if it is like a salt where they will dissociate into two different components. And I would definitely give you a question that would tell you that, right? That would say, what is the boiling point of a salt water, at this point, and I equals 2. Okay, I would give you I. Now you can calculate I if it's sodium chloride, that just associates into 1 mole of sodium and 1 mole of chlorine. And so the I factor is 2. Okay. But I would definitely, I would tell you that if you needed to factor in I.
So we would just look to see if you say that it dissociates into multiple parts. Okay.
Or if I say I is 2, right? So if you don't see anything referencing I mean, there might be a question where I say predict I for sodium chloride, just because now we've gone over it a couple times. You know that if it's sodium chloride, that's going to have an it's going to have a Van't Hoff factor of 2. Okay. But generally, I think the OpenStax textbook doesn't even have I in it because they don't even go into those problems. So I wouldn't make you have to figure that out. But all good questions. Okay, TF, this is what we're dealing with in lab today. Freezing point depression. So just as solutions will increase the amount of heat needed, because remember, what is a boiling point of something? A boiling point is when the vapor pressure is equal to the atmospheric pressure. And if you do anything to drive down the vapor pressure by adding something else to it in solution, it's going to require more heat to then get that equivalent vapor pressure that will then be equal to the atmospheric pressure to then increase or facilitate boiling. Okay. And it all goes down to the intermolecular interactions going on between the solute and the solvent, right? It's distorted the interactions in the solvent. We've distorted the interactions in the solute. Remember, in order for a solution to occur, you have to break apart the intermolecular interactions between the solute and the solvent. And then they have to come together because like dissolves like. So we're changing these intermolecular forces. We're changing, therefore, the properties at which they behave, because a solution is now a homogeneous mixture, right? It's no longer pure. So the freezing point depression is the same equation as the boiling point elevation, same concepts, except the values are going to be different, and we're going to subtract it from the temperature because it's decreasing it, not increasing it. Okay. So for instance, here's a problem, Aaliyah, where we have 1 mole of sodium chloride dissociates into nearly 2 moles of ions in solution. If there were a problem where you had to use the Van't Hoff factor, then that would explicitly say it in the problem. Okay. This is showing you different Van't Hoff factors. And again, it's all relative to the dissociation, right? So if we have, for instance, magnesium chloride, right? That's magnesium bound to 2-chlorine. And if they all dissociate from each other, now you have 3 ions in solution, 3 moles. So now it has a Van Hoff factor of 3. Now in reality, it's not quite exactly that. It's 2.7, just like sodium chloride isn't exactly 2, it's 1.9. But we are able to expect, we use those expected values in our calculations, most typically. Okay. So what's the freezing point of a 1.7 molal aqueous ethylene glycol solution? All right. So delta TF equals KF times molal. And we have this being 1.7. We just need to look up ethylene glycol, which I don't see it in here. So let's look that up real quick, see if we can find the KF for ethylene glycol. If anyone else finds it before me, just shout it from the rooftops. I got 1.86. Okay. And then look at those units, right? KF is technically 1.86 degrees Celsius per molal. That's not very legible, so let's try it out here, right? 1.86 degrees Celsius per molal times, what was it, 1.7?
Yep, 1.7.
Thank you. And so molal cancels, and we get whatever those two are. 1.86 times 1.7.
$3.162.
3.162, or I guess 3.2 in this case, degrees Celsius. That is what it's lowering the temperature. So now, what do we subtract that from? We know the freezing point of water is 0 degrees Celsius, right? Because this is an ethylene glycol and water solution. I think it's general rule of thumb, if we don't tell you what it's being dissolved in, if we don't tell you what the solvent is, it's going to be water. Okay. So 0 minus 3.2 is a negative 3.2 degrees Celsius. And that is why we put antifreeze in our engine, okay? Because it lowers the freezing point of the water that it mixes with, so that it doesn't freeze and expand and break our engine. And there's different grades, you know, same thing with windshield wiper fluid. You know, you can buy the low temperature windshield washer fluid so that it doesn't freeze. It just has stuff in there that makes it a solution that changes the freezing point. So it's 250 now. I'm going to then skip through here. Oh, I gotta skip the vodka one. That's a nice problem. Maybe I'll save that for a practice exam or something. Let's do one more osmotic pressure problem. If you guys want to go, of course you're free to go, because it is now time for a lecture to end, but I'm going to stay around for a little bit longer and just do this one last problem. The osmotic pressure is equal to molarity times temperature times universal gas constant. Okay. That's the osmotic pressure. Remember, the osmotic pressure is the pressure required to prevent a solvent from passing through a semi-permeable membrane. And reverse osmosis, as we talked about in lab today, is the additional pressure applied to drive that actually through across the semi-permeable membrane in order to purify water, for instance. Okay. So if we have this problem where the osmotic pressure in ATMs is, oh, they're asking for that. Okay, so they're saying, what is the osmotic pressure if we have a solution that has a volume of 0.750 liters and has mass is 5.0 grams of methanol in water at 37 degrees Celsius. What is the osmotic pressure? So we know that osmotic pressure equals mRT. So we have temperature at 37 degrees Celsius. So we have our T. All we need to do is figure out our M, which we can, because what is molarity? Moles per liter. We have our liters. We just need to convert the grams of methanol into moles. And then we just put in our point, what is it? 0.08206 gas constant, and bada boom, bada bam. So see what you can do with this. You need to look up the molecular weight of methanol. Yeah, because they know not to come in here. Molecular weight of methanol. I guess maybe you need to know what methanol, well, you can just Google it, but methanol is the simplest of alcohols, the kind you don't want to drink, the kind that will make you blind, wood alcohol, the kind that the bootleggers would sometimes make as a byproduct when trying to make ethanol. So anyway, 1 carbon, 4 hydrogens, and an oxygen. Molecular weight. I've got 32, 1 mole over 32.04 grams. So if we take 5 divided by 32.04, we get 0.156 moles. Okay. Now, osmotic pressure is equal to, let's write it down here. Osmotic pressure is equal to the molarity, so 0.156 moles per 0.750 liters times gas constant 0.08206. Double check that, make sure that's right. And then times temperature, 37 degrees C. And then units, liters, what are the units for this? I think this is liters times atmospheres times mole over moles K. Double check that. I think that, yes, moles K Do we need to convert this to Kelvin? You bet your life. So that's 37 plus 273.15, which is 310.15 K. All right. Now our moles cancel, our Kelvin cancels, our liters cancel, and we're left with atmospheres, which is what we want for osmotic pressure. And so what is all that? 0.156 divided by 0.75 times 0.08206 times 310.15. I've got 5.29.
I got the same thing.
Woo! All right. Okay, that's it. That is our osmotic pressure. Okay. Now, again, if there's anything you guys if there are any of those problems that we kind of glossed over still that you want to work on and come to me with during office hours tomorrow, I'm happy to do that. Otherwise, I will potentially see you, I guess, I don't know, maybe a week from now, maybe Tuesday. Okay. So if there are any questions in the meantime regarding, this material, the midterm, anything in general, how you feel like you're doing so far, if things are sinking in, if things aren't sinking in, please let me know. Like I said at the beginning, feedback is crucial for my success and your success. And so the only way that I can get a gauge for the pulse of how this class is going is to hear from you guys. So keep that feedback rolling in. Do the lab today and tomorrow. Any questions, please feel free to let me know, and take care. Okay.
Dr. Franz?
Yes, Gum. What's up?
Just look at the schedule and the syllabus for the when the midterm would be. But I just want to ask you, when would the midterm you plan on us taking? Probably like next week, or is it going to be this week? Well, I don't know.
No, it's scheduled for next Tuesday
Okay.
at 1 p.m. So during the normal lecture time. Now, someone said in the comments that so Chase had said that Sean let you guys start it whenever you wanted. That's fine with me too. Since we won't have lab that day, what I'll probably do is I will just give you guys a certain amount of time to do the exam, and you can start it whenever you want, and just keep in mind that you have that allotted time. Okay, so if it's 2 hours, then if you started at 10 a.m. on Tuesday, you got to finish it by noon. If you started at 1, you got to finish it by 3. Okay, but I'm not going to make you take it at 1. Okay, you just got to take it sometime on Tuesday. Okay.
Sometime on Tuesday. And would the deadline would be like midnight, just like a regular assignment? Or is it?
Yeah, I could do that. I could make it any time on Tuesday by 11:59 p.m.
Sounds good. Thank you.
Well, yeah, I hesitate to do that. I mean, so for the lab Thursday morning, yes, it will be an ICA. I initially had it in the syllabus as a journal club, but I don't want you guys to have to worry about reading a paper. So we will just plan on having an ICA that day. I hate for there to be too much potential for crosstalk. So I think that you know, making it the very end of the day might be a little bit, might be a little bit, you know, nothing against anyone personally, but, you know, if someone took it at 10, theoretically, they could say, oh yeah, the test was like this, and talk to somebody else. And I'm not saying that you would talk to anybody or anything, but I think maybe just to keep that window small, I'll have it due by 5 o'clock, by 5 p.m. Okay, guys, any other questions? Okay. Well, I'm happy to stay on for a few more minutes, but you know, you guys free to go. Take care. And again, come see me tomorrow morning or tomorrow afternoon. If any other questions come up. If you don't want to do it then, or if that doesn't work out for you, there's also Sean's office hours and Erinna's tutor hours. And you can message me, you know, that kind of thing too. So whatever works out for you, we'll try our best to accommodate it. Okay. All right.